So the last piece of the puzzle here is just going to be walking through the test driver implementation, which is what sets all the wheels in motion, literally for both the client side and the service, and also look at the performance of the different approaches because we're going to time them and see how they do. So looking at the client side, looking literally at the PrimeCheck test, Spring Boot test client, and you can find that, as always, in the EX2 project, in the WebFlux folder, in the Live Lessons GitHub repository. So here we are in that repository, in that project. Let's take a look at PrimeCheck test. So you can see that PrimeCheck test is a Spring Boot test that will launch the PC server application, which is this guy over here. And it's going to use the port that's defined as part of the application properties. So that's how it gets connected. We'll see in a moment. And we've got two auto-wired fields, one that's auto-wired to the PCClient parallel flux class, and one that's auto-wired to the PCClient concurrent flux classes. We just looked at those, so we don't have to look at those again. We've got a run tests method that we mark being a test, so it'll run, and that'll start the service as well. We parse the arguments that are passed in. You can see here we're going to disable debugging messages, and we're going to generate 5,000 large random odd integers. Sorry, 500. Let's change that to be 1,000 just for kicks, and that'll give us a little bit more time to see the differences between these different approaches. We then go ahead and we generate the random integers. And this is kind of a fun little helper method that I have used in the past. Let's just go take a quick look at it. So what it does is it takes a count and a max value to generate, and whether or not we want to only generate odd numbers or let the numbers be odd and even. Because we're doing prime number checking, there's really no point in giving it even numbers since they're obviously not going to be prime. So what we do here is we generate an infinite number of random ints within a range that will generate some duplicates. Doesn't really matter for this example because I'm not memoizing anything, but just it's a fun thing to do in general. And then what we're going to do is if we're only generating odds, then we're only going to let odd numbers pass through. And of course, a number that mods by 2 that is not 0 is odd. We limit ourselves to this many of those values, and then we box the results up and return a list of all these things. So that's how we get ourselves a list of numbers, which in this case are going to be odd numbers. So we've got a list of random odd numbers, and we're going to reuse this list for all the different strategies that we're testing because we want to have them comparing apples to apples. We want them to all work on the same data. It would be unfair if some got different values that might make it faster to compute whether the numbers were prime. So then what we're going to do is we're going to make 4 calls to a helper method called timeTest. We've seen me use this particular pattern before for tests. And first, we're going to test individual calls using parallel flux. We're going to test individual calls using concurrent flux. We're going to test the list calls using parallel flux. And we're going to, or not the list calls, the flux calls using parallel flux. And then we're going to test the flux calls using the concurrent flux. So all those things are going to run one at a time, and we're going to time them. And we also take each of those lists, we take the list of random integers and turn it into a flux so we can pass fluxes into this thing. And then when we're done, we're going to print the results out in order from fastest to slowest, so you get to see which ones work best. So here's the time test method. You can see that it takes in a function that will map flux to flux. That's the thing that we're computing. Takes the list, or sorry, the flux of prime candidates and the name of the test. So we record which test we're running, and then we go ahead and we time how long it takes to perform this particular test. So we take the test, which comes in as a function, and we apply it, because that's what you do with functions, and we pass in the prime candidate's flux, and we get back a flux. Now, what we're going to do next is really important. We need to make sure that we block the caller until all the processing is done. Otherwise, if we don't put this block call here, this thing will return right away, and we won't get an accurate count of the time it took to actually do the test. So here we go. We apply this. That runs asynchronously. We get back a flux of integers. For testing purposes only, we collect that flux of integers into a mono to a list of integers, and then we block on that list until all the results have finished. So that's how we do that, so we get the right results. And then when we're done, just for kicks, we go ahead and we display the results. And this is actually kind of fun. It shows off some other interesting features of fluxes. So you can see what we're doing here is we're going to take the prime candidates, those are the things we ask the server to check for primality, and then the results that come back, which will be this flux, and we use the zipWidth operator. And what zipWidth does is it marches through the two fluxes one at a time, getting an emission for each, and it assumes those the same size, which they are. And it's going to take each pair of fluxes, one from the prime candidates, one from the results, and it's going to zip them together like a zipper. And what comes out of that is something called a tuple. And a tuple contains the pairwise combination of each of the elements from each of the sources of fluxes. So then we go ahead and we say the result for the prime candidate value equals the result that came back after we got the result back from the server. So we just do that in a little debugging action. Do on next is an action operator. And we just block until everything's done. So that goes ahead and processes everything here in a way that demonstrates zipWidth, which is a very fun little helper method. OK, so that's the end of stuff. Let's now go ahead and run the tests. So remember, I'm running this on my laptop. We've got a 10-core Apple MacBook with the A1 Max or whatever was hot about a year ago. And you can see that we start doing the individual calls with the parallel flux with 1,000 of the same values as we do for concurrent flux. Then we do list call parallel flux and list call concurrent flux. I should really call this flux call, not list call. And then we get the results back here. And let's go see who won. So remember, this is done from fastest to slowest. So interestingly enough, the list calls for the concurrent flux actually turned out to be a little faster. Kind of interesting. And in fact, you can see here, well, this also, keep in mind something else here. Let's try running those tests again. The other thing to remember is that the first time anything is called, it takes longer. It has to be started, and there's some cache warm-up that has to take place. So sometimes you have to run things more than once. I'm not sure if this will actually give us a different result because we didn't keep the server running when we ran the test again. If this was a production system, obviously unlike the tests, we would have the servers up and running so that after you do the first call, they would be nice and warm and ready to go. But you can still see in this case that the list calls were a little faster for concurrent flux, not by much, but a little bit. But in this case, the parallel flux started operating a little faster. But those are like in the noise in terms of being difference. So the bottom line is that parallel flux and concurrent flux typically work roughly about the same. And so you just have to decide whether you like the parallel flux programming model better than using the flat map concurrency idiom. So that's the end of that particular case study.